Okay, today what I would like to go over is hybridization. And this has to do with blending of orbitals. So we're going to be revisiting S and P and D orbitals that you guys learned about in the electron structure unit. So here at the top, I have an analogy. I used to have a dog named Astro. He was a Bassador, and that was a combination of a Labrador and a Basset Hound. So he had the short legs of a Basset Hound and kind of like the happy-go-lucky nature of the Labrador. Okay, so when we look at hybrid orbitals, they're kind of like the same idea. We're mixing, in this case, sp and sometimes d orbitals to make hybrid orbitals. And the idea behind this is to allow us to get the angles, the bond angles that we are seeing with the geometries of the molecules. So when we look at molecules, we see that when we look at something like ammonia in H3, it has a trigonal pyramidal structure with a little bit less than 109.5 degree angles. But when we look back at when we learned about the S and the P orbitals in electron structure unit, if you guys remember, the bond angles, the angles between those orbitals were about 90 degrees. So they would not allow us to explain the geometries and the bond angles that we see with molecules that are in nature. So what we have then is how scientists have tried to explain the bond angles which we see in nature, which, as you remember, have to do with the electron clouds trying to get as far apart from each other as they can. So we explain this using hybrid orbitals. So the first type of hybrid orbital is an sp hybrid orbital. And here we're combining an s orbital with a p orbital to make two sp hybrid orbitals. So they are each like with a little lobe and a large lobe. And when they overlap in space, they allow us to form a linear bond angle. So 180 degree angle. So these are hybrid orbitals. This process of forming these is called hybridization. And this allows us to get a linear molecule in that 180 degree angle that we see with some of our molecules. So on this slide, I actually want to show you guys kind of how this is occurring, just to make it very clear to you what's happening here. So what we actually see happening here is we see that, and I'm going to draw this onto the slide, that we have two hybrid orbitals here. This is one of them. And I'm going to make the other one a different color so it stands out more. And then we have a second one. And these are overlapping with each other at the center here to form that linear shape. But this shape here, remember, this is actually two overlapping sp hybrid orbitals. Okay, so I want to show you an instance where this occurs in nature. So what we see is that beryllium chloride, if you remember, has a linear shape. And this, to form this linear shape, it forms sp hybrid orbitals. Okay, the next type is Sp2 hybrid orbitals. So here we take a single s orbital. We take two of the p orbitals, and these overlap to form three Sp2 hybrid orbitals, which allow us to form this trigonal planar shape with 120 degree angles, bond angles. Again, we have three hybrid orbitals. So we have one hybrid orbital here, and then we have a second hybrid orbital. And then I'm going to do the third one in yellow. And then we have a third one here. And that forms, like I said, this 120-degree bond angle, and allows us to bond with three things. Okay, so an example of this is boron trifluoride. So that has a 120-degree bond angle. To have that kind of bond angle, we use the Sp2 hybrid orbitals. Okay, the next type is Sp3 hybrid orbitals. So here we take a single S, we take 3 of the p orbitals. This forms 4 hybrid orbitals. So they overlap in space to allow us to form the tetrahedral shape. So this allows us to get about 109.5 degree bond angles. So here you can imagine we have one Sp3 hybrid orbital, and then we have another hybrid orbital, and I'm going to do one in yellow, and then I'm going to do one in green. And remember, this is like a three-dimensional shape here. So maybe this one is that blue one's coming out at you, the yellow one's coming out at you, the green one's going away from you, and the red one's going up. So that's 4 hybrid orbitals, allowing us to get that tetrahedral shape. So an example of a molecule forming this is carbon tetrahydride, which we have as a tetrahedral shape, and that is where we see this Sp3 hybridization. Okay, so now remember there's only 3 orbitals in the p sublevels. So to get more areas, regions, we now have to start using the d orbitals. So to allow us to bond with or have 5 different regions, we have dsp3. We take a single d, a single s, and 3 of the p orbitals. This allows us to form 5 regions in space and allows us to get that trigonal bipyramidal shape. To allow us to get to 6 regions in space, we have D2sp3. We take 2 of the d orbitals, 1 of the s, 3 of the p's, and this allows us to get an octahedral shape and have 6 regions. So again, this the dsp3 will be 5 hybrid orbitals. D2sp3 will be 6 hybrid orbitals. Okay, so just some examples of these. We have 2 instances of an expanded octet. Here we have phosphorus pentafluoride. We see the dsp3 hybridization. And then we have sulfur hexafluoride, where we see the D2sp3 hybridization. Okay, so the hybridization only occurs when you have an atom bonding, and it will also depend on what other atoms the atom is bonded with. So what we see is that, for example, carbon will do Sp3 hybridization, but we also see Sp hybridization, and sometimes we see Sp2 hybridization. So it depends on what carbon is bonded with. So I want to show you guys a table, but I'm going to show you how to how to figure this out. But if you're someone who likes to refer to a table, you can refer to this, but I also want to point out the patterns here in this table. So what we see is if you look at each of the forms here, Abn notation, if you count up the B and add the N to that, what we see is that with AB2 that has 2 regions off of our central atom, we need to have something that forms where we have 2 hybrid orbitals, which would be Sp. So Sp would match up with AB2. When we have 3 regions, either 3 bonding or 2 bonding and 1 non-bonding, we have 3 regions total. We would need something with 3 regions with the hybrid, which would be Sp2. When we have 4 either AB4, 3 plus B3 plus 1N, which equals 4, 2B plus 2N, which equals 4. That will require 4 regions, which will be our Sp3. 1 plus 3 is 4. We have 5, either AB5, 4 plus 1 is 5, 3 plus 2 is 5, or 2 plus 3 is 5. We require 5, which is DSP3, so we have 1D, 1S, which add up to 2, plus 3 Ps, which is 5. We have 6, either AB6, or 5 plus 1 is 6, or 4 plus 2 is 6. We will need 6 regions. D2, which is 2 plus single S, which adds up to 3, plus 3 Ps, which adds up to 6. That will give us 6 regions. So we can use this kind of pattern to kind of correlate which forms will require which hybridizations. So I want to practice this using a worksheet that you guys worked on a couple nights ago. So I'm just going to pause this for a second and bring that up. What we're going to do now is we're going to look at some of the problems we worked on a couple days ago and now look at the hybridization of each of these. So if we look at water, what we need to do this is to think about the Abn notation. So we see here oxygen is our central atom. It has 2 hydrogens bonded to its Ab2 and then 2 lone pairs N2. So remember, this is a bent structure. But if we look at the number of regions, we have 2 bonding and 2 non-bonding regions. So we have 4 regions that we're using. The hybrid orbital that will allow us to have 4 regions is Sp3. Remember, 1 is single S and 3 Ps also add up to 4. So remember, the total number of regions has to add up to the total number of hybrid orbitals, which are that we have. If we look at this one, we have carbon dioxide. We have a single central atom. We have 2 things bonded to that. It says Ab2. This has 2 regions. This is a linear structure. The hybrid orbital, which will also give us 2 regions, is Sp. This adds up to 2, a single S and a single P. We have 2 regions here. Now, when we have a diatomic molecule like this, we do not need to use hybrid orbitals because we don't really have a bond angle. We don't have a central atom. So remember, nitrogen has a partially filled p orbital. And when those 2 nitrogens bond together, their partially filled p orbitals actually overlap. So we would just use p orbitals in this situation here. Look at beryllium dichloride. Here we have A, B, 2. Again, this is a linear shape. And we have 2 regions here. The one that allows us to have 2 regions is Sp. Now, if we go down here, look at boron trifluoride. We have A, B, 3. We have 3 regions. This is a trigonal planar shape. The other one that gives us 3 regions for the hybrid orbitals is Sp2. Look at this one here. We have a carbon with 2 hydrogens and 1 carbon bonded to it. This is going to be AB3 also, trigonal planar. And also Sp2. We look at this one. We have a carbon with 3 hydrogens and 1 carbon. It's AB4. We have a tetrahedral shape. and this will have to be sp3. Now here we have carbon, oxygen is diatomic. Carbon has a partially filled p. Oxygen also has a partially filled p. That will be a p orbital. We don't need to use hybrids there. Same thing with oxygen gas, p orbitals. So this is how you do these kind of things. You have to think about your Lewis dot structure. So it's really important you draw that correctly. You have to think about your geometry. So you have to carefully consider your geometry. And then you have to add up your bonding and non-bonding regions for your central atom. And then figure out that. And then come up with a hybrid that has the same number of regions. So again, if you have something with two different central atoms, you're going to have to figure out two different hybrids. So if we come down here, look at carbon. Carbon itself would be sp3, because sp2, because you'd have an ab3 notation, which is trigonal planar, and then sp2 hybridization. This one here would be ab2 n2, which would have 4 regions, and that would have an sp3 hybridization, because a single s and 3 p's will add up to 4, so that will give you those 4 regions. Okay, so good luck with these. If you have questions about any of these, please feel free to email me.